Hi all, welcome to CS 176B Lecture 4. So today we will be talking about network operating systems. But before we talk about network operating systems, let's try to recall what we learned in the last lecture. So in the last lecture, we talked about how forwarding abstraction requires a programmable data plane. And we talked about how this data plane can be implemented in either software or hardware. We also learned about the characteristics of these data plane targets. Something that is implemented in the software, such as OBS, are very flexible, but they are slow. Things or the targets that are implemented in hardware are fast, but they're inflexible. And we also learned about PISA, which stands for Protocol Independent Switch Architecture, and that helps strike a balance between this flexibility and scale. So it is more flexible than the fixed function switches, and it is faster than the software switches, right? So with that, let's now move forward. And the learning objectives for today's class are that we will be trying to understand what type of different network operating systems exist for software-defined networking, right? And in the literature, you might see that not everybody refers to them as network operating systems. Sometimes people just call them SDN controllers. And this is an artifact of the discrepancy that we had in the terminology in the community in general, and also because the idea of network operating systems was something which was not very common to the networking community. It took some time. I don't think there's consensus even now, but those two terms have been used interchangeably over time, right? So don't get confused when I say network operating system, and when you read papers, people call it an SDN controller. Other than that, we will be also talking about the fundamental scalability challenges that exist in the design of these software-defined networking control plane. And we'll be talking about how different implementations of network operating systems address these challenges. More specifically, we'll be digging into ONIX, which you have already read as part of your reading assignment. But we'll also be talking about ONOS, which is an extension of build up on top of ONIX to address the limitations of ONIX. We will eventually be covering two other systems called Candu and Devoflow. But given the interest of time, in today's lecture, we won't be able to cover them, but we will cover them in the next few lectures. So let's try to get some terminologies in place, right? So we know this figure. There is a host. There is a bunch of switches that are connecting these hosts with each other. So we know what is data plane. And then we have a concept of network operating system. And this network operating system is using southbound APIs to communicate with the data plane targets, right? Or the programmable data planes that we have. The network operating system is providing a global network view, and that is the instantiation of the distributed state abstraction that was one of the underlying abstraction for software-defined networking. So the network operating system is responsible for providing this global network view to the users, right? And then it offers a northbound API through which these control applications can interact with the operating system, and then they can write their logic of how they want the network to behave, right? So there are some variants that are worth understanding and visualizing. So in this setup, and especially when we think about NOX, which is an implementation of a network operating system, the idea is that you have one physical server that is connected to all the switches, and it is talking to them via the southbound APIs. But as we will see in this today's lecture, that it is possible that there might be more network operating systems in a way that maybe those other instantiations don't really talk to each other as much, but just talk among each other. Or there might be some instantiations that we have two different network operating systems that are talking to a different subset of the network, and then they talk through each other using the east-west bound APIs, right? So an example of this can be, you can think of the left side of this cloud being located in, say, LA, and the right side being in New York, right? So if you have these type of devices too far from each other, you probably want a network operating system which is a bit local to each other, and then they communicate the state information between each other using the east-west bound APIs. So now that we understand, the basic terminology of the network operating system, let's try to understand the underlying scalability challenge. So as we know that, the key idea or the key driving force for software-defined networking is flexibility, right? And OpenFlow is an instantiation of that. And OpenFlow allows match action rules for a very expressive flow space, right? So flow space can be expressed as a combination of 13 different header fields, right? So the flow action or the match action rules that exist or that can exist in the open flow switches is very flexible, right? So there is a huge number of possible rules that one can write in the data plane memory, right? But as we know that, like the switches that are, especially the hardware data planes, they have very limited switch memory, right? So the switch memory, you can think of the TCAM or SRAM, and all these memories, because they provide like really fast access. So I think, because of those, the costs are relatively high. I don't want to get into the details of like how exactly these memory blocks are implemented, but you can check how SRAM is actually implemented, and it is like really costly to like expand SRAM, the cost of building a huge SRAM versus DRAM is like significantly different. So that's why the SRAM is suited for implementation in the hardware data planes, but at the same time, it is very expensive. So you will only have a limited amount of memory available in the data plane switches. Now, so as you can see the tension here that, at one end, the software-defined networking allows very flexible set of rules. So technically, you can have a lot of rules, and that requires a lot of switch memory. But at the same time, these switches are not capable of hosting or holding that much flow rules, right? So what will happen is that, the network operating systems will be responsible for handling the packets, right? So when a packet comes in and it does not find any rule that matches its requirement, then it will, go up to the network operating system, and then the software implementation will be responsible for finding a map, right? So just think of an example that you have, say, an application that requires a forwarding state that requires, having some 10 million forwarding table entries, right? But if your switch can only support, say, 100,000 forwarding table entries or match action table entries, then there's a mismatch, right? So, like that is basically 1%, oh, not even 1%, 1/1000th of a fraction, right? So that is basically a very small fraction of the total number of flows that will actually find some entries in the data plane, right? So a lot of packets will actually be going from the data plane to the network operating systems to figure out, okay, what rule should I follow? And maybe, like the way these type of systems have been designed, those rules can be cached in the data plane based on the requirements, right? But it's still depending on how the traffic composition is, what type of rules you have, the initial instantiations of these network operating systems realize that the number of updates, the number of packets that they have to handle is very high, given this, limited memory and need for a large number of forwarding table entries, like that fundamental tussle that resulted in too many packets going to the network operating system, right? And as we know that processing packets in a user space is slow, so that has a significant impact not only on the amount of workload for these processors, but also in terms of or the overall performance of the network, right? So if a significant fraction of the network traffic is actually going through these CPUs to decide what needs to be done, that has a significant impact on the performance, right? And I just want to point out one example that, like in the discussion sections, we will be teaching you a simple, network controller and how that works. So you will notice that when you are sending some traffic, the first packet or, like the first instance, when the packet goes through the data plane, it probably has no, rule in the data plane. So it will go to the network operating system, try to figure out what rule is best for it, and then that rule will be cached. So the following packets that belong to the same flow will have a lower latency, but the first packet will actually incur a high latency, right? And this is because that packet had to go through the network operating system. It was processed in the user space, and the delays are much higher than what you can do in the data plane, right? So now that we understand the scalability challenge, or maybe I should elaborate that scalability challenge a bit more, that when you are sending too many packets to the control plane, you're overwhelming it in two ways, right? One way is that you're overwhelming the amount of resources that the controller has, right? Because if it has to handle so many updates all the time, then like it will require a lot of CPU cycles to process those number of packets, right? But at the same time, it also stresses the control channel. And you can think of it as like, the bandwidth that is available between the data plane and the control plane that will also be overwhelmed because there is so much of traffic coming in from the data plane to the control plane and trying to figure out what needs to be done with it, right? So in general, if you think about it, by design, or the intrinsic constraints that we have in the problem, this is a scalability nightmare, right? You want a lot of flexibility that requires a lot of rules, but you don't have that much of space. Then you will be sending a lot of traffic from the data plane to the control plane, and that kind of does not ends up well, right? And that will require really smart, intelligent observations and solutions that will help us scale the system. But naively building something which is like, okay, if you don't find anything, just come to me as a controller. I think that type of naive approach does not work here. So what can we do, right? So one approach that the community came up with was the idea of using distributed network operating systems, right? And this is something which must be familiar to some of you because you have read the ONIX paper and you understand the idea of distributed network operating system. The key, thrust here is that we can increase the controller capacity by using a set of distributed network operating systems, right? So it is admitting that this problem is real, and we need a lot of resources for the network operating system. And the good way is that you don't have to map an operating system to a physical server, right? An operating system can be distributed, or this network operating system can be realized and instantiated using multiple physical servers, right? Of course, that helps with the reducing the stress on the control resources. Like per server, the amount of stress is relatively low. But these specific techniques don't necessarily reduce the stress on the control channel, right? And ONIX does address that to some extent, and we'll talk about it. But I think some of the solutions that we will discuss later are more effective in reducing the stress on the control channel. So ONIX is one system that you've already read, and there is an extension to ONIX called Open Network Operating System, or ONOS, and that was introduced in Hot SDN, which is now called as SOSR in 2014, right? So ONIX came out in 2010. It was something which is already deployed at Google by that time, and some of the OpenFlow controllers at Google were built up on ONIX, right? So 2010 is a bit too early in the phase. And you will see in terms of the abstractions and the design choices that the system made, you can see how the community was just still grappling with this new toy at hand. They were just trying to figure out, okay, what is the right abstraction? What are the right mechanisms? You already noticed that when you read the ONIX paper, but we'll try to appreciate them more in this lecture. But this is not the only approach. There is other approach where the idea is that you can actually vertically decompose the network operating systems based on the functionalities. And the insight was that all the information that is coming out from the data plane need not go not all the entire control plane needs to know about all this information, right? So it was leveraging this inherent hierarchy that exists in the network topologies to decompose the functionality that the control plane supports, and was trying to cache the local operations as much closer to the data plane as possible. So Candu is one of the solutions in this space, and we will learn more about how that is helping scale the network operating systems. But such an approach does reduce the stress not only on the controller resource, but also on the channel, because it's kind of pushing some of the high frequency actions of handling high frequency updates closer to the data plane. And the third approach was to, which is very similar to the second approach, which is offload the control plane operations to the data plane itself, right? So here the idea is that the switch also has a CPU, also has an operating system. So if we are smart enough about something, but that switch CPU is very limited in terms of computation, right? So what you need to do here is to make sure that the actions or the type of task that you offload are such that they can benefit the limited compute capabilities of the CPU that we have on the switch, right, or in the data plane. So there are multiple papers in this research direction. DFANE is one that came out of Princeton, but DevoFlow is another research paper in this direction. That's something that we will cover later, not in this class. So let's focus on the approach one, because that's something that you folks also read in greater details for the reading assignment. So, ONNX is one such instantiation of distributed network operating system. ONNX view of the network system can be divided into these four different components. One is the physical infrastructure that has the switches, routers, etc. And then there is this connectivity infrastructure, which you can think of the channels which are used for sending the messages between the upper operating system and the lower physical infrastructure. And ONNX is a piece of this ecosystem where it's a distributed system that is running the controller, right? And then there are this control logic, which you can think of the network management applications that are sitting at the top of ONNX, and they are using the northbound APIs to interact with ONNX, right? And the connectivity infrastructure is basically leveraging the southbound API, right? So ONNX is talking to the physical infrastructure using the southbound APIs. And an example of southbound API is OpenFlow, right? So let's try to visualize this architecture a bit more. So, the physical network infrastructure will consist of multiple switches, right? And then these switches, on top of these switches, we have this management connectivity infrastructure, right? So connectivity network infrastructure, which is facilitating communication between switches and the physical servers that are running the controllers. And then you have these physical servers that are providing the compute capabilities or computing prowess to the operating system. And on top of each of those switches sits an instance of ONNX, right? So ONNX will have these three different components. One, which is responsible for interacting with the switch. The second, which is responsible for interacting with the other network operating system. And then something called network information base that we will discuss later is also part of the ONNX, right? And then ONNX provides these northbound APIs for the network control logic, which can write these control applications. Say, for example, if you are trying to use a smart way of handling ARP request, then a network control application can be responsible for okay, if an ARP request is coming in, what should be my response to that ARP request, right? So what should be the response? Maybe rather than the devices actually responding to the ARP request, maybe this controller can actually reply to it, leveraging the network information base, right? So that is just one example of how or what type of applications this network control logic can write. So in terms of abstraction, ONNX offers the global view, which, as you recall, is one of the primary requirement for the distributed state abstraction, right? So the distributed state abstraction says you have all these devices that are distributed in the network, but I don't really care about how you get this information, but I want to make sure that when I'm writing a control application, I should have a global view of the network, right? Irrespective of the mechanism. So the control application technically should not worry about how this global view is created, but all it cares about is the nature of that global view, right? And this global view observe and control a centralized network view, which contains all physical network elements. Then there is this abstraction of flow. And as we know that the flow is basically defined as or is identified by 5 tuples. And those 5 tuples are, the source IP address, destination IP address, source port, destination port, and the prototype, right? Protocol type. So protocol type is either this is TCP or UDP, and then source port, destination ports are specific to the implementation of TCP, UDP, and then we have source IP address and destination IP address. So the first packet as well as the subsequent packets with the same header are treated in the same way, right? So different packets within the same flow might vary in terms of, say, the TCP specific fields, such as the congestion window or option fields, or whether it is an acknowledgement, the acknowledgement number or sequence number. So those fields can vary, but the other fields that I talked about within a flow are invariant, right? So source IP address is not changing, destination IP address is not changing. So all the decisions that are applied for a packet or the first packet are applied on all the consequent packets within a flow, right? And why we are differentiating between first packet and the subsequent packets, because when the first packet comes in, it is possible that we don't know how to handle this packet, right? So in most likely this first packet is going to the controller, and then the controller is going to eventually the control application, and then control application is based on whatever logic has been implemented, it will decide that what type of action needs to be taken for this flow. and then that action will be communicated to the network operating system, which will then be pushed down via the southbound APIs or the OpenFlow protocol in the data plane. So when the second packet or third packet comes in, then this rule is already cached in the data plane, right? But the first packet it is likely that it won't have any rule in the data plane for it, and it might be going to the controller, right? And this kind of contributes to the scalability challenge that we were talking about earlier, that if there are too many unique flows that are there in the network, and that kind of talks about the composition of traffic that we have, then we will have a huge amount of load at the controller. But say if a network is such that we only expect very few new flows to come in, all the flows are kind of predictable, and it is possible to cache most of the rules, or at least cache rules for the traffic that are contributing most in terms of volume, then you might be able to reduce the load at the controller. But in general, given the limited memory that we have in the data plane, a new flow might not see an entry, and that's why there will be delay in the decision making for the first packet compared to the subsequent packets, and that will also contribute to the load at the SDN controller or network operating system. Right? So flow, I think I just wanted to dig deep into this flow thing, because flow is very fundamental to the abstraction in the software-defined networking, because all forwarding decisions are typically made at the granularity of flow, right? And there is defining flow is a bit abstract, right? You can the 5 tuples is just an example, right? So you can make decisions at coarser granularity. You can say only decide at the destination IP address level, or you can decide the combination of some of these subset of fields, or you can be very, very specific about, maybe the 13 fields that are supported by OpenFlow. So you might write a specific rule which is specific about each and every field, right? So the different abstractions exist, but I think, whatever is the definition of flow, all the packets that belong to that same flow will be treated equally. And then we have this abstraction of switch. It has flow tables, and those flow tables will have a match action, structure. So it will be matching one of a subset of headers. And then for each of them, there will be an action which is defined. But at the same time, the OpenFlow has this counter abstraction. So it will also be counting that how many packets actually match this rule in the data plane. And then it's an event-based operation. So whenever there is some event that is going on in the network, then those updates are triggered, from the network, or by the it can be top down or bottom up as well. So in terms of API or the application interface that it provides, the Onyx provides a global view, which is represented as a network graph. And as you can recall, that is something which is very fundamental to network operating system, that its primary job is to instantiate the distributed state abstraction. And the key requirement is that there should be a network graph abstraction, right? So I should be operating on graphs, not on the mechanisms of how this graph can be generated, right? And this is something that we covered in lecture 2 as well, where we considered the example of Dijkstra algorithm, where the OSPF router implementation, the specification, was spending a lot of time talking about the mechanisms of how a consistent view can be created by each and every router, and then very small portion of how you can use Dijkstra algorithm to compute the shortest path, right? So now the job of network operating system here is to offer this network graph abstraction, such that all these applications can just operate on the network graph and don't worry about the mechanisms of how this graph can be generated, right? So this is a power of abstraction. We are abstracting away the details of the mechanisms by which this network graph can be generated, and the control applications just need to see what that graph is and make decisions based on that, right? In this graph, the nodes are representing the physical network entities, and the developers are writing their control applications over this network graph. And the example of things that they can do with this graph, they can write some flow entry, they can enumerate the list of ports on a particular node, and then they can also register for some updates, right? So something changes for this device, then the control application can actually put a register for updates, and all those updates will be received by the control plane, right? So then the control application is aware of something. Say, for example, an example of an update can be that whether the link is up or down, right? So if there is an event which says that a particular link is down, then this event can be if the application is registered for it, then it will know that this link is down, and then based on that, it can make some decisions to maybe reroute the traffic if a particular link is down. Right? So the network information base is something which is inspired from what already existed in the networking community. So information bases was something which is very intrinsic to the networking community in the past. Typically, there were two information bases that were very common. One was the routing information base, RIB, and then there was something called forwarding information base. So forwarding information base was you can think of these set of forwarding rules that were implemented in the data plane. And the routing information base was, you can think of the information base which has all the forwarding state, but in the user space, right? Or kind of like the control plane of the network. So the routing information base was converted into forwarding information base, and that's something how typically original or old routers used to operate. And there was another information base called management information base, or called MIB. So you had MIB, RIB, and FIB, right? So from that perspective, you can think that the idea of NIB, which is network information base, is a bit incremental. But at the same time, from abstractions perspective, it is very powerful because it is providing this graph on which these control applications can operate, right? And as we were discussing earlier, that the key piece here is the node, which represents a physical entity or the physical element in the network. And it has these associated fields about the ports and then the forwarding tables that are associated with the node, right? One thing to note here is that the updates to the network information base are asynchronous, right? So that basically means that if I am writing two set of updates on different portions of the nib, there are no guarantees in terms of ordering that if I write, if I do a write operation on one part and the write operation on the other part, so there is no guarantee that there will be an order that will be followed or the sequence in which these updates will be implemented, right? So if I say that, okay, update the forwarding state and drop all TCP packets on a particular switch, right? And then I have another rule which says okay, maybe something which is applied before that, which is already dropping some other traffic, right? So maybe it is dropping HTTP traffic, right? So, I have some abstraction about, okay, if these updates are applied in sequence, then my network state is going to be stable. But the ONNX does not provide me with those type of consistency guarantees, right? So to do that, the network control application has to implement its own logic of handling the synchronization issues, right? So ONNX does provide a synchronization primitive. So when I put an update, I can register for an event which tells me whether, or callback which tells me whether this has been implemented or not. And once it is implemented, then I can technically put a lock and say that, okay, update this part of the nib, then wait for a confirmation that it has been implemented before making any other change, right? So that is one way in which I can ensure consistency. But as you can imagine that, not providing these guarantees pushes the complexity towards the control application itself, right? And something that is not desirable from building, less complex distributed systems, right? So, I mean, the software-defined networking was not designed so that you can push the complexity of distributed networks to distributed servers that are, or the distributed data plane to a distributed control plane, right? That's not the goal. The goal is that the control applications that are eventually running the network, they should just have a consistent, simple view of the network, right? A centralized view of the network. The mechanisms of how you do it is something which should be abstracted away, right? But given this approach that the ONNX had, there was still, when I'm writing a control application, I'm still engaged about these synchronization issues. And that is something which is undesirable, but that is also an evolutionary thing that, the community was just growing, figuring out the right abstractions, right mechanisms of how this can be implemented is still a hard thing to do. So, you don't start with a perfect system, you start with systems that are good enough, but at the same time, you always are cognizant about the limitations of the existing system such that you can iterate and improve. And you also should have this future vision or the ideal goal in mind, that what an ideal system should look like, right? So you're always making some step-by-step progress towards that goal. The first system that you will build will not be perfect, but in future, others can build up on that system to make things even better. And this is a design pattern that you will see in most of the papers that you will read, and something that you might want to appreciate when you're filling out the review forms as well, that there are some papers that will be exposing this ultimate view of what a system should be. And then, maybe they will be able to achieve that goal, and maybe they will admit that, okay, we're not completely there, but this is a step in the right direction, right? So I think like some papers will be modest enough to admit that, they have not achieved the ultimate goal. Or some papers will be, they will change the goalpost and say like, okay, this was not really our goal was something simpler and we achieved that goal, right? So there is a difference in how you read those papers. I appreciate the papers which are honest and are visionary, that lay out that, okay, what is the grand plan that we want to achieve, and then lay out that, okay, how is this moving in the right direction, but still not, achieving the ultimate goal, right? And that leaves, like, that becomes a communal effort that you build up on the existing set of works, so that like over time you are able to achieve that eventual goal, right? So I digress, but I think like, this perspective will help you when you're reading the review forms and trying to compare the papers that the systems that we are reading with the other existing works. So continuing on the discussion for network information base, NIB is the focal point of the system. Like the state for applications to access, so it is some state that is desired by the application developer so they can access using the NIB. The external state changes are imported into it. So right, if there is some other part of the NIB that has some updates, that they get imported to it, and then the local changes that an application is making that get exported out of it as well, right? But as we discussed earlier, that there is this intrinsic scalability challenge, and those scalability challenges do haunt the design of Onyx system as well. More notably, I think like, this NIB abstraction will overrun the memory in one server. And I think the paper did a good job of differentiating between the type of state that will be problematic in terms of memory requirement, right? So they had this distinction between switch state versus forwarding state, right? So switch state is, you can think of that as a topological information, right? So how many physical switches do you have? How many ports are there on that switch? How many ports are active? How many ports are not active? And as you can imagine that, like the dynamism for this type of state is very low, right? So you're not adding new switches every 1 second, or like, turning up or down a particular port every 1 second, right? So this is not a very high frequency thing. Depending on the type of network you're operating on, like if you are at QCSP, maybe these things are changing at the granularity of, a couple of months or maybe years. If you are running a very high-end competitive cloud network or a data center network, maybe these things are changing at the order of days, right? But not at the order of seconds. So, but compared to that, the forwarding state or some other telemetry related information, those are very dynamic in nature. Those are very transient in nature, right? So the forwarding state is a bit derived thing that you observe something and then compute a forwarding state, but forwarding state is very huge. And that is something that we discussed earlier as well, that because forwarding state is so huge, that's why you can't actually put completely in the data plane as well. So that's why you put a cache of it in the network operating system. But even one network operating system might not be capable of handling the entire forwarding state, right? So you distribute that or partition that across multiple servers. The other metrics that I was talking about were the telemetry related information about the link utilization or the number of packets or counters and all those things. This is something which is very dynamic, very changing. Some of this information is stationary, which means that they fluctuate within a particular range. Some of them are non-stationary, that is they're kind of like always increasing. Like counters is an example of like things that are always increasing, and the link utilization is something which is kind of like stationary, right? So in addition to that, I think not just the memory, but I think like the CPU as well as the bandwidth for one server will also not be enough to handle all the updates, right? So as we were talking about earlier, that if you just have one physical server and if you have like 100 switches connected to it, it will get overwhelmed in terms of handling all the updates. But if that 100 switches scales up to 1,000 switches, like things will just get significantly overwhelmed. So you cannot just continue to add or make this network more and more complex, add more and more components and expect just one server to be good enough to handle all that, right? So there are overheads in terms of the bandwidth, that is the channel between the physical switches and the server, the physical server. So that's a bandwidth constraint. And then the CPU, that when these packets or updates enter the network operating system, then like it has to do a context switch, handle all these packets, decide what these packets are saying, and then update the state, make decisions, right? So this is a CPU overhead. And then we talked already about the memory overhead, that the amount of memory that is required is also significantly high. So these are the scalability challenges that are obvious, and it kind of like makes a lot of sense that one server should not be used for implementing a network operating system, right? Especially the networks which are relatively more complex in nature. So you want a distributed approach, and that's what Onyx has been focusing on. But even in distributed approach, you still need the right abstractions. So the one abstraction that Onyx embraces is partitioning. So what it does is that decouples the switch state from the forwarding state, right? And then it talks about partitioning the forwarding state, right? So it partitions the forwarding state and assigns a partition to each of those Onyx instance, right? So the way it partitions is that it is logically separating networks into different groups. Think of a wide area network that is, say, supporting networks like Google, right? So they will have data centers in multiple cities, and so the wide area network, which is connecting these different data centers with each other, they will have a bunch of switches at each location. And you really don't want one physical server that is managing all these switches, right? So you want to partition things. And in this case, when you have such a huge geographically distributed wide area network, then the partitioning is very, very obvious, that you want to club together all the physical devices which are in close proximity to each other, right? So that is one way in which you can think about partitioning of the forwarding state and assigning those partitions to the Onyx instances. Each of these instances do maintain a consistent switch state. And as we were talking about earlier, that because the switch state or the topological information is very, very invariant over time, it does not change much. So given that, all these instances are capable of maintaining a consistent state, and they do that, right? Because you don't really want to operate on a partial state in this case anyways, and given that the overhead of maintaining a consistent state is very low, so that's a low hanging fruit that they can grab, and they grabbed it, right? The other metrics that I was saying earlier, that link utilization, or in general think of any type of telemetry information, they're all fast changing metrics, and for that they embrace this approach of using a distributed hash table, right? And this is one example of how they're using an existing technique that already existed in the distributed systems world, and they're embracing and applying that in context of the software-defined networking, right? And then the control applications are responsible for updating the local forwarding state, right? So basically control applications are monitoring the switch state, or they have insight about the switch state. Then they are monitoring these updates that are coming in from the distributed hash tables. And based on that, if they're registered for some of these events, then based on that, they will have to update their decision, which means that they will have to change the forwarding state, right? So they can locally compute a new forwarding state, and then they can rely on the OpenFlow or Southbound APIs to make sure that those changes are implemented in the data plane, right? So this is Onyx, approach in terms of principle, in terms of partition. But this is still not very scalable. This itself is not very scalable, and this is this is coming from the fact that there are so many low-level updates that are part of the network operating system, any small changes in the link utilizations and all those things for every port. If I'm somebody, if I'm a network operating system instance running at Chicago, I don't really care about some small low-level details about a port or link utilization statistics in Los Angeles, right? So the idea that they have embraced is that, let's use the principle of aggregation, that there is some natural hierarchy that exists between these network components. So rather than reporting, each and every node in that hierarchical tree, maybe let's just report what is the statistics, general statistics for the root of that tree, right? And this aggregation principle is not very unique to Onyx. This has, as you probably read in the paper, this has been embraced by other protocols in the networking as well. So this is a natural, progression from the protocols and data structures that were designed for some other application, then they were adopted by Onyx, right? So in summary, that like the building blocks do exist. I think like a lot of time systems research or any applied research focuses more on how you can build up on the techniques or systems that were developed for some different use cases. How can you use it for your problem, right? Which might sound a bit patronizing for people doing systems research, but I think like I won't argue that that is easy, right? And as you can see that Onyx is a good example that it's not like the distributed system techniques and implementations didn't exist, but even when the best of the best working at Google and other companies, they were trying to build Onyx, and the kind of like abstraction that they could come up with were not as clean as they are right now, right? So you can see that building these things, even though there are some existing tools and techniques that do exist, like adapting them for specific use cases and that require some domain specific insights is a non-trivial thing, right? So that is a lot about, tells you a lot about the systems research, that when you look at things in retrospective, things look obvious, right? And you just think that, hey, why didn't anybody thought about it at the first place, and why did we go through this process of one iteration over the other, and like things improved over time, but if you look at a single iteration at a time, you will think like, hey, these people didn't really had those bright ideas, right? So I think like that tells you a bit about the intellectual challenges of how these systems are developed, and it takes time for ideas to converge and better abstractions to come, right? And this is probably not just limited for systems, but I am like an expert on systems and networking, so I can tell you how that has evolved in the networking and systems community. But I'm very sure in programming languages or security or some other areas, the same principles or same design patterns are visible there as well. Anyways, I digress. Let's get back to the Onyx approach. So they focus on aggregation, but they also focus on the they also have to handle the consistency issues, right? So because they're partitioning the state, so they want to provide some consistency guarantees there as well. So the control logic typically dictates the consistency requirement. For example, they can specify that I think like there was some knobs about the import-export fields that you can configure. That is something that will tell you that how much should you care about a particular state in the nib. And they offer two type of options. For slow changing state, such as topology or the switch state, they offer this replicated transactions using SQL. And for the link utilization, they use the distributed hash tables. Anything that is kind of like fast changing, they use distributed hash tables. But as you can notice that the control logic here or the control application is actually responsible for resolving conflicts if necessary, right? So they provide this abstraction that how a control application can extend the existing implementation so that they can handle the consistency issues. And this falls back to the point that I was making earlier, that this is not a clean design, right? This is not really what you want the network application developers to focus on. Their goal should be that a consistent state is available to them. When they read something, when they write something, there are consistency guarantees that are offered to them as part of the system. But that was not something which Onyx was offering. And that's something as an evolutionary thing, that these things take time to evolve. And that was reflected in how Onyx was designed at that time. And this is something which was developed in 2010. And, as for, like to recall, these ideas about software-defined networking were in very, very nascent stage at that time, right? So these abstractions, those clarities that we talk about were not very clear. And building these systems, learning from these systems, people kind of like observed and iterated and improved on it, right? So the Scott Shanker's talk that we covered in lecture 2, or in fact, lecture 2 was completely built up on that talk, was delivered in 2011. Right, and this paper, this Onyx, was actually written and published in 2010. So probably it was built in 2007, 2008, right, or maybe 2009, right? So I think there is an evolutionary nature to this problem, and what I'm emphasizing on this again because we tend to think that somebody who's doing research in this area knows it all, and that has been my personal experience as well. When I was talking to Scott Shanker for some of my research projects, and I said like, hey, this is a problem. And probably know how to solve it. And his response was that I expect you to solve those problems. I don't have solutions to all the problems myself, right? So he's like, this is how research evolves, that when we start, or like, you folks are as an undergrad students, like this, like reading all these papers might be overwhelming, and you might think that, oh, like somebody has already written an ONIX paper or ONIX-like paper, and then, like they know everything about the problem, and they were like, so knowledgeable about all the nuances of building or adapting a distributed system so that you can build distributed network operating systems. But that's not the reality. The reality is that converging on some good abstractions and then building good mechanisms that like amplify those abstractions is something which is very, very hard, and it takes a lot of time, right? So even you can do this type of research, and I think like systems research is relatively, like, it is a lot of labor, but at the same time it is also very rewarding, right? So I hope that when you read this ONIX paper, you felt to some level that given the exposure that we had on this topic so far, you were able to follow the logical argument that was presented in the paper, and you can like track how those ideas are evolving in the ONIX system itself, from Knox to the ONIX, and then as we will cover, like how those get even better in the next iteration, which is ONOS. So to summarize, ONIX did a fantastic job of instantiating the distributed state abstraction. That was one of the key requirements from SDN's perspective. The scalability challenges required embracing a distributed systems approach here. Like, it's not a perfect system. It lacks a cleaner API for control applications. The control applications are responsible for resolving consistency issues, and they have to consider the scalability implications of whatever logic they write. So this is, as I've been saying so far, it's kind of like a reflection of community's struggle to find the right abstractions and mechanisms, which is non-trivial. So I'm not saying our community is dumb. I'm just saying, like, coming up with the right abstractions and mechanisms take time, and it's a lot of hard work. So now we will move forward and talk about, briefly talk about ONOS, Open Networking Operating System, to understand, like, whatever the gaps were left by ONIX, how ONOS tries to fill it, right? So as we discussed, that finding the right abstraction for distributed network operating system is something which ONIX tried, but it didn't do a fantastic job or a perfect job for it, right? And like, there are a lot of distributed system techniques and implementation that already exist. So ONIX tried to adapt some of them, but it was not completely embracing all the existing repository of work that exists in the distributed system community, right? And like, just to let you know, the distributed systems community is quite advanced and mature, that like coming up with some new ideas or systems for distributed systems problems is tough, because like the algorithms, the abstractions, they're very mature in nature, right? So like there has been a lot of work, and like if I dig into the trajectory evolution of distributed systems area, that might be a course by itself. But what is worth noting here is that there was a lot of, or there is a lot of maturity in the distributed systems community in terms of the principles and abstractions. I think the research is all about like new constraints and requirements that come in, and that require like revisiting those abstractions and modifying or adapting them, or maybe coming up with a better mechanism to realize those same set of abstractions, right? So I think like it's an exciting area by itself, but it's relatively mature, especially when we look at the software-defined networking. The community was or is still trying to find the right abstractions mechanisms. But because we are embracing this distributed systems thing, so like it makes sense to leverage the existing set of techniques and implementation that are already there. So ONOS did that, right? So ONOS did a fantastic job of adapting the techniques and implementations, and they focused on developing an open source network OS. And I think like this is something which is worth emphasizing, that like around the time when ONOS was developed, there were competing platforms that were available. So ONIX was one, but ONIX was not publicly available, right? And then there was Knox. Most of the researchers were building their applications or systems on top of Knox. And POX was an implementation, like a Python implementation of Knox. So, like from prototyping perspective, a lot of researchers were focusing on POX. From production perspective, there were a couple of targets available as well. like Open Daylight was one, and I guess Floodlight was one, and each of them had their pros and cons. But like in the open source community, and Ryu was one of them. In the open source community, there were very few targets which were actively maintained, were very performant, and like easy to work with. So for a lot of my research, I focused on POX as well as Ryu. Because these were Python implementations, and I, like in research, you want quick prototyping, and then you focus on performance. So like from performance perspective, good solutions didn't really exist, but from prototyping perspective, good solutions did exist that were there in the open source community. So the natural trajectory that was taken was to build something which is very performant, something that can be deployed in production, but at the same time, it is flexible enough or open enough so that others can embrace it as well. So ONOS was kind of like an answer to it. It focused on different building blocks that already existed. So in terms of implementations, we had the distributed storage systems like Cassandra and RAM Cloud. So Cassandra and RAM Cloud were already relatively hot topics of research, but they were still relatively mature as well. So like figuring out the right ways in which they can be adapted is something that was an interesting research challenge, but something which made a lot of obvious sense, right? Then then this is the bunch of systems on distributed graph databases, because we are building a like a partial view of graph on each of those instances. So providing a centralized view requires like embracing some implementation that already exist that offer distributed graph databases. Then distributed event notification, that like you want to do the like all these applications are getting registered for different type of events, and you want to do that in a distributed manner. So Hazelcast was one solution that was kind of like prominent in this space. And then it also requires distributed coordination service, right? So a particular switch, for fault tolerance reasons, might want to connect with multiple physical servers or physical servers providing the operating system service. But at any point of time, you probably have one of them as the leader, right? So for fault tolerance, like if one goes down, then you might want to fall back to the backup option. But like for fault tolerance reasons, you are a switch is connected to multiple physical servers, and the zookeeper is something which kind of like facilitates the leader selection and all these internal mechanisms, right? So as an application developer, I should not worry about all these things. But I think like these like a simpler abstraction does not mean that the mechanisms that are providing the simpler abstractions are also simple, right? Those mechanisms can be complex as long as they are offering certain guarantees or consistencies. Then and that simpler abstraction, they're acceptable. But we should not expect a simpler abstraction means simpler implementation, right? That is not always connected with each other. And then it also leveraged existing techniques that were there in the distributed systems community, distributed hash table, which was already embraced by ONNX, but then a bunch of consensus algorithms, algorithms for detecting failures, checkpointing, and transactions. So this is an architecture for ONOS. Here, when you look at the OpenFlow Manager, let's try to kind of like go up. So as you can see that OpenFlow Manager is the one which is managing a subset of switches. And it is one which is responsible for physically interacting with the switches, right? And then on top of it, we have the distributed key value store for storing the state. And then there is a networking specific graph abstraction that ONOS developed. And then there are these network view API that are offered to each of those applications. Like now the applications are not tied to any like individual physical server or like ONNX like instance. This is something which is like it has a global view. All the missing abstractions that were kind of like part of ONNX have been resolved with ONOS. So it provides that, it offers that global view that was the basic tenet for software-defined networking. So that goal was achieved or instantiated with the ONOS network view API. And this is one example of this global network view. The applications are using this set of observe and program mechanism, or like read-write mechanisms for observing the current state. And the way it is expressing the network state is it is kind of like expressing the topology, which is switch port link, as like with these things. So like a blue rectangle is representing a switch, and like all the ports connected to that is basically the other set of nodes in this graph, and then the links that are connecting these ports. So I think like that view is covering the topology, and then on top of it you have the state in terms of the network events, which is like whether the link is down or whether there is a new packet coming in. And then there's a state from with respect to the flow state, which is like, what are the flow tables, what are the connectivity paths between point A to point B in the network, right? So these are the abstractions that the Open Networking OS or ONOS was offering, and this is something which was designed as the original view of software-defined networking, and ONOS is an instantiation of that view. I'm not saying that it is complete and it has no limitations, but this was something which was published in 2014, and it has evolved significantly since then. And right now there is a new version of it called Micro ONOS, and that is specifically designed with the service level abstraction, which is, or the microservice abstraction that is gaining a lot of popularity these days, where different components or different modules of the systems are developed as microservices that interact with each other. So that helps significantly with the scalability of the system, and that's something which is you can consider that as a new version of the ONOS system. So to summarize the ONOS, I think it builds up on ONNX. It instantiates the desired global view at scale. It leverages the existing distributed system techniques and implementations to address the scalability and reliability issues. It is open sourced, which means that it is actively maintained, which also means that it is widely used, right? So ONOS is something which, from production perspective as well as from research perspective, it is widely used. And I think using a system for research that is also widely used in production is also very, very helpful, because it helps with the transition of ideas from academia or research ideas into practice. So this brings us to the end of our lecture today. The takeaways from this lecture are that network OSs instantiate software-defined networking's distributed state abstraction. By design, scaling these systems is non-trivial, as we've learned today. We discussed 3 different approaches that can be used. We discussed one of them in great details, called the distributed network OS approach. We talked about 2 implementations of that approach. One is ONNX, the other is ONOS. In the next lecture, we will try to cover the 2 other approaches, which was the hierarchical approach and the offloaded approach. One system is called, or one instance of that is called Candu, the other is called Devoflow. And from there, we will be transitioning to network virtualization, and how network virtualization, what are the basic instantiations of network virtualization, and how that, help create the NCP platform for, virtualizing the entire, virtual, data center networks, or the multi-tenant data center network that was part of this company called Nicira, which was acquired by VMware, and that's a billion-dollar success story, right? So we will talk about the fundamental ideas that were driving the design of NCP, and how that virtualization was relevant and useful in the multi-tenant data center environment. All right. So with that, we will be ending today's class, and I hope that if you have any questions, you will be coming to my office hour on Friday. I look forward to talking to you folks then. Thank you.